Welcome back from the weekend and happy Tuesday. Today we'll switch gears and turn our attention to the Poisson distribution, which deals with the occurrence of events in time. But before we begin, some administrative bits. The reading has been added to by the 3rd of November, which is a Tuesday. Please make sure you've gone through section 3.4.5 in the main text, pages 65 through 67. It's not a lot, but make sure you are keeping up. Project number 3 will be due on the 29th, this Thursday, concerning reliability simulation, in that you'll be comparing the equivalence expression for a circuit, mixed circuit, and the simulation of the individual components and their interactions. Okay, so this following picture is an overhead camera that's used in a retail establishment, and it's used to track the customers that enter the store or leave the store. Now, we have an overhead camera picturing like what I call the entry box of the store. As customers go from outside of the store to inside the store, it tracks them. And as they go from inside the store to outside through the entry box, it tracks them. And I'll direct your attention to the upper right-hand part of this video. We have the number of people, accounts, who have entered the store and the number who have left the store. The difference between the two is the number of people that are in the store. And so one of the things we're interested in is the likelihood of a certain number of events. In this case, the event is somebody who's entered the store. Now, in fact, you could use this kind of information to make informed decisions from the data by modeling this system and then asking that model what number of people, customers, are coming into my store, and then use that information based on data you've observed from a system like this, use that information to decide how many employees, for example, that you might hire. And so the tracking of people in time, as well as time and space, is useful for all sorts of things. So here, let me set my pen. Here in the upper picture, we have an overhead view of a camera. We can track customers going through a store. We have a customer from this display walking out, proceeding, and going out through the doorway. And you can take this sort of information over time and actually measure how much time each person is spending in a certain location of the store and plot that aggregate information, and that's what you see here on the bottom left, in the form of a so-called heat map. And so those counts that are higher get a color that's closer to red, one end of the spectrum, and those places that have lower counts get a cooler color closer to the blue end of the visual spectrum. And so this heat map is used to depict those portions of your retail space where people tend to walk and spend time at. Now, why might a retail establishment care about that information? Because it means that people are looking at things more in some locations than others. So certain shelf space is more valuable. So you want to put certain items that you want to sell in places where more eyeballs are looking at it. You can also track with this heat map over time those items that are selling well. I mean, certainly you could get that from the cash register. The most modern computerized cash register systems give you that information. But you can also see, given popular items, get people on purpose to walk through your store, because the more they walk through your store, the more likely they are to see things. You want to get so-called eyeballs on product. And so if you had something that was really popular in one section of the store, maybe you move it to another section of the store, and that then forces people to walk across the store more, seeing these products. And that's why when you go to things like supermarkets, you see the peanut butter is not right next to the jelly. And you might wonder, well, why in the world would they not put the peanut butter next to the jelly? Well, because they want you to walk across the store to get the jelly after you've gotten the peanut butter. And if you have them both places, you're just going to grab one, grab the other, and then leave, versus walk by the store. And then walking by the store, you see more of the items in the store, and you're more likely to make those impulse buys. It's about collecting as much cash from you as they can. And moreover, here in the bottom right, we have another use of this temporal tracking. We're looking at the number of customers that are in line at a register. And so you could use something like this to make an informed decision, model it, and then sample from that probability, and then use decisions from that model to tell you how you need to hire employees or have staffing levels at your cash registers for certain times of the day. All right, so here's another example of a heat map. Is an overhead view of a heat map, and we have another view, cutaway 3 picture of this heat map, a heat map superimposed on a picture. And we see the doorway to a store. This is a cell phone store. And then we see the routes that people take where they congregate. So they congregate over here, they congregate less so here, they congregate quite a bit over here. And so you can use this to your advantage in deciding where to place products so that you can perhaps get people to walk around more and see more of the merchandise for sale. This is a device called an eye tracker, and what it does, it has a forward-facing camera, and it also has a backwards-facing camera, and this reads the position of your pupils to determine what you're looking at on a screen. And this eye tracker looks at events in time, where your eyes are pointing and where your eyes come to rest in habituating or looking at a particular part of something that's in front of you. And so that's used for things like packaging design. Here we have a heat map, and these colors represent the amount of time someone's eyes spend looking at parts of the package in temporal order. And so for this packaging, we see that the first thing someone looks at is the actual meat product that's inside of this container. And then they look at the label. And then after that, they look at the sticker that talks about the origins, the source, and the type of meat product this is. And so with this type of eye tracker system, this temporal set of events in time, you can actually use that to inform your packaging design. If people are going to look at the meat first, you want to have a nice wide window so that people can see as much of the product prominently displayed as possible. And you notice here the stickers are kind of pushed off to the side here, and the product description and barcode, scan code sticker is much bigger than the description, because that description is the third thing that the person's eyes attend to. All right. And so here's another example of a heat map. This is a Best Buy, right as you walk through the entry, and you can see the heat map is much higher for these items as you first come into the store. And then you also, your attention goes upwards to the signage to look at what types of products are available where. And so the idea then with this is if your eyes are going to attend to certain parts first, those are the higher value parts of the store. And you want to place things there that the store really intends to sell a lot of. And so you'll notice when you go into a Best Buy, you first walk through the entry box. When you come into the store, you'll notice the items that are right there, right after you come through, are typically the high value items. And then you always have the cell phones right behind it. Cell phones are recurring revenue, and it's high value items. Okay. So let's take a look at our probabilistic tool, probability, that describes stochasticity specifically of the sort where the events occur in time. So here we have the famous physics eyeball, right? And this physics eyeball you talked about in physics, you observe something. And you observe something, and here's something, an event occurs, and this dog looks a lot like my dog, but nonetheless, you observe some event, something happens. And so you have a period of time, or a so-called window of observation, during which this event occurs. So I'm going to abstract the occurrence of this event that you see using one of these little dots, or meatballs, if you want to call it that. And this delta t represents that period of time during which you observe the occurrence of that event. And so each single observation we depict, and it occurs through some period of time we're calling delta t. And it doesn't matter how big delta t is or how small it is. It could be a second, could be in 10 milliseconds, could be 5 minutes, could be 15 minutes, could be 1 hour. It doesn't matter what delta t is, but the only prerequisite we're going to set here is that delta t must be the same each time. And so we continue over several windows of observation delta t occurring in time, the number of observations for some event. And so here we have delta t, and again, delta t must be the same each time. In the first occurrence window of observation, we see 2 events. In the second one, we see the event occur 3 times. In the third, we see the event occur 4 times, and so forth. And so we depict this temporal event occurrence diagram, we call it the Poisson configuration, to help us with our notation. And we're going to develop the probability mass function for the Poisson. And then we're going to derive this Poisson and show that it is a probability and it adheres to the law of total probability. And so the first question we pose, how might you measure something that occurs over a period of time? Well, we have something over time. This is typically called the rate. And that rate represents, on average, the number of occurrences that you see in windows of observation of size delta t in time. And so the rate then refers to something that occurs per unit time. So you have to kind of standardize what this unit time is. And we can also say per period of time or per unit time. Now, of course, I'm going to use synonyms so that when you go off in the literature and read about this, you're going to see many different names for the same thing. So I want to make you conversant in the different ways that people talk about these windows of observation delta t. So sometimes they're called modules of observation. Sometimes in the literature they're called windows of observation. So the rate R for some event that occurs in each module of observation is what we're interested in. And in particular, of interest is this average rate. And we're going to call that average rate, we're going to call this R. Okay, so we have our rate R. And of particular interest is how likely we are to observe some number of occurrences of the event within our module of observation delta t. And if we can get this, we could use something kind of like stick breaking to generate, okay, this time you got 2 events, this time you got 1, this time you got 3, and so forth. And so of interest is how likely we are to observe some number of occurrences of the event in time in a module of observation. So let's try to think about some examples. Now, of course, at the outset in the introduction, I gave you some of them. You can think about customers that walk into your store. On average, throughout maybe the first half of the day from, say, 8 a.m. to noon, you have a certain rate. And then from noon, say, to 8 p.m., you have another rate. Now, certainly you could represent the rate in terms of larger windows of time, or if it works better for your coffee shop, maybe in the early morning at 7 a.m., for about 3 hours to 10 a.m., you have the morning work rush. Everyone's coming into that coffee shop to get their morning coffee. And then the rate drops from 10 a.m. to maybe noon, and then you have the lunch rush from noon to 2. And then from 2 to 4, it drops, and then you maybe have an evening rush. And so it doesn't matter what this delta t is. We're interested in just our window of observation being consistent, because at the end of the day, we're after the average rate. Okay, so some examples. Customers that walk into your store, students who visit the dining hall. Now, certainly at DSU, in normal times, pre-COVID and post-COVID, it's a lot larger numbers, but nonetheless, students who visit the dining hall, it occurs in time. For every 5-minute window of time, you see maybe 10 students, then maybe 2 students, and then maybe 20 students, and then maybe 5 students. Likewise, and this is a particularly interesting one, packets that arrive at a router. Now, if you know about the traffic profile for a router, this can help you do things like determine what is the amount of buffer size you need in order to store those packets. And so packets that arrive at a router, that is absolutely a stochastic quantity. And the number of packets per unit time that arrive at the router for some delta t, that's our rate. And now you're looking at the average rate. Okay, so let's define K. And K is going to be the number of occurrences of interest. And so we're interested in K equals 2 in this first window of observation, k equals 3 in the second window of observation, k equals 4 in this third window of observation, and lastly, k equals 3 for this last window of observation. And so k is going to be the number of occurrences of the event of interest, and r is going to be the rate, our average number of occurrences in our windows of observation. And so this is the probability of observing k occurrences of the event in a window of observation. Given an average rate r, that probability of seeing k events is going to be r exponentiated to the k power upon k factorial and upon e exponentiated to the r power. So there we go. That's our mass function. But where exactly does this come from? How does that work? Well, let's think about this. What in the world does this mean? Well, let's go back to the binomial distribution. And for the binomial distribution, we said x is distributed as, that's how you pronounce this squiggle, tilde, x is distributed as a binomial distribution, and that represents the probability of x many successes given n trials, where the probability of a single trial is p. So this is our binomial. It's defined by n, the number of trials, and p, the probability of success for a single trial. Okay, so when we think about this binomial, we're going to use the binomial to give us this expression for the Poisson distribution, our probability mass function for the Poisson distribution. And so for the binomial, well, there's the mass function for the binomial. Probability of observing x successes is n choose x times p to the x power. So these are for the individual probabilities for the successes. There are x many of them, times the probability or rate for each one of the failures. 1 minus p, which is also nicknamed q, as we said before, raised to the n minus x power. So these are the successes, and these are the failures. Okay, so this is the probability mass function for the binomial. And what we'll see is that the Poisson is nothing more than a special case of the binomial where n is really, really large. In fact, n goes to infinity. So let's talk about this. So we said from before the expectation in a previous module of a binomial random variable is np. Okay. This is our average number of successes. And so the average number of successes, if you think about a success as being the observance of an event, well, we're going along in time, going along in time. All of a sudden we have a success. Check. We're going along in time, going along in time. All of a sudden we have another success. Check. We keep doing that, going along in time. All of a sudden, success. Going along in time, success. Going along in time, success. Success. Okay, you get the point. So E equals NP for the binomial is the average number of successes. And so if we talk about average number of successes, we can think about that average number of successes as the average number of the occurrences of the event. And so this E, the expectation of a binomial random variable, it looks just like our rate, where the rate is the average number of observations in each of these modules of observation that are consistent over time. Now, again, I stress that delta t doesn't matter how big it is. Delta t could be 10 milliseconds. It could be 10 hours. It doesn't matter. 15 minutes could be 5 minutes. So this expectation sounds a lot like our rate. And in fact, it is a rate if we consider the occurrence of an event in time as a success. It's absolutely the same thing. So we're going to set our expectation, NP, equal to the rate that we talked about for the Poisson. If we think about occurrence of an event as a success, it's exactly the expected number of successes. Okay, so if R is equal to NP, do a little algebra, we get P is equal to R upon N. And so P probability is equal to the rate divided by N. And if you think about this, this is exactly a proportion. It's the number of successes divided by the total number of trials. So absolutely a rate is mapped directly to this idea of the expected number of successes. If you think about the occurrence of an event as being a success over time. Okay, so let's now take our expression for the mass function for the binomial distribution, and we're going to substitute everywhere we saw p, we're going to substitute this r upon n. And so remember, we had a p to the x, so we substitute r upon n to the x. We had 1 minus p to the n minus x, so we have 1 minus r upon n to the n minus x power. So now, if we assume this idea of a success is some event that happens in time, what we're missing is this part about what it means to happen over time. And so how much time do we assume? Because the binomial distribution talks about the number of trials is n many trials. And so this idea of over time, we need to relate this idea of over time to this idea of n many trials. So how much time do we assume? Well, at every single period of time. So at this first period of time, did we success? Yes or no? Success? Yes or no? Success? Yes or no? Success? Yes. Success? No. 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 Yes. And so at every single possible period of time, we measure what happens. And either one, we see an observation, that's success, or we don't see an observation, that is a failure. So in mapping to the binomial distribution, this Poisson configuration, this idea of over time, well, how many times do we do this? We do this as time marches on. That's what the rate means. And if we do it as time marches on, well, the number of periods of time or points in time that we can measure is going to be infinite. And so this n is going to be infinity, and we can actually solve this expression and arrive upon the mass functions of the Poisson by taking this special case of the binomial, substituting r upon n for the probability of the occurrence, because that's our rate, and then letting n go to infinity to represent the fact that we're evaluating for n many trials, where a trial is conducted at every single point in time that is possible. And that n many trials is infinity many trials. Okay, so time marches on. So that means now we're going to take our expression for the probability. We substituted the binomial probability mass function. We substituted for p. That's r upon n. And now we're going to take care of this infinity many trials part. So we're going to let n go to infinity, take the limit as n goes to infinity of the probability of this binomial where we've substituted r upon n for the probability. Okay, so let's look at this. If we make n really, really big, this is what the value of this expression becomes. This, we will show, becomes this probability mass function. And that's what this probability for number of successes k, assuming an average rate r, will turn into. And so the Poisson distribution is nothing more than a special case of the binomial where we're performing n many trials every single moment in time. Okay, so we have this limit, and I've rewritten this limit, and this expression is for probability p of x for the binomial distribution. And we did that substitution r upon n for p, and we let n go to infinity. And so now the result of this limit, as n goes to infinity, is going to be the probability mass function, or the PMF, for the Poisson. Okay, so let's take a look at this, and we'll note a property that if you take the limit as n goes to infinity of the product of two functions, that's the same as the limit of the first function, f of x, and the second function, g of x, and multiplying those resultant limits together. And so if we want the limit of this expression up above, we're going to take the limit as n approaches infinity of n choose x, the limit as n approaches infinity of r upon n to the x power, and the limit of 1 minus r upon n to the n minus x, and we're going to multiply those three limits together. All right, so let's now take each one in kind. So let's look at the limit as n goes to infinity of this first term, n choose x. And so if we expand what n choose x is, that's n factorial over x factorial n minus x quantity factorial. Now, if we do this out, that's n times n minus 1 dot 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 times n minus x plus 1 times n minus x factorial over n minus x. It should be an x factorial over x factorial. So the n minus x quantity factorials, they cancel, and we're left with n times n minus 1 times dot 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 times n minus x plus 1 over x factorial. And now, if we multiply these terms together, well, we have x many terms. There's our first term, second term, up to and including my x term. Now, if I have those x many terms, if I were to apply something like the FOIL rule is for two factors, I multiply them together, I get an n times n times n times n times n x many times. All the other terms in this expansion of this polynomial are going to have an exponent that's less. And so that first time, n times n times n times n x many times, I'm going to have n to the x power. Now, all the other terms, they're going to have some coefficients, but they're going to have n to some power that's less than the x power. So it's going to be stuff less than n to the x. Now, of course, if n is going to get really big, and I have a term that's n to the x power, and stuff that's less than n to the x power, as n gets really big, the impact of that stuff that's less than n to the x is not going to matter much. This n to the x power is going to dominate. And so I can just drop off that stuff that's less than n to the x power and just consider the n to the x over the x factorial. Okay, and so I write then the limit as n goes to infinity of n to the x power plus stuff less than n to the x power upon x factorial is just n to the x power over x factorial. So that's my results. I'm not done yet. This is my result for the first term. So now let's look at the second term. Well, I'm just going to set that aside. Right? If I have limit as n goes to infinity, that's just r to the x power over n to the x power. And I'm going to set that aside. That's my second term because I want to take the limit for the first term and then the limit for the second term, limit for the third term, and then I'm going to multiply them together, show what happens as n gets really big, as n goes to infinity. Okay, so now I have these two parts. I have my n to the x over x factorial. That was from limit for the first term. I have my r to the x upon n to the x. That's my limit for the second term. And now I look at this third term. Okay, and so I have this expression. And if I look at this limit of the product of these two first terms, something interesting happens. Well, if I multiply these limits together, okay, well, one of the things I can do, well, I have a numerator, I have a denominator. And so this is n to the x power over x factorial times I have r to the x power over n to the x. So that's just n to the x power r to the x power over x factorial times n to the x power. I can swap the n to the x because multiplication is commutative in the denominator. And I notice also that n to the x, numerator, n to the x denominator. So I can cancel, and that leaves me with r to the x upon x factorial. And so that's exactly what I do. I swap the denominators because multiplication is commutative. N to the x over n to the x is 1. And I'm left with the limit as n goes to infinity of r to the x upon x factorial, which is just r to the x upon x factorial. And so the limit of the product of the first two terms is just the product of the limit of the first term with the limit of the second term. And if I do that, I get that limit as n goes to infinity of r to the x power upon x factorial. Okay, so we've taken care of the first term. We've taken care of the second term. So now let's turn our attention to this third term. Now, this third term gives us we're going to multiply by the limit, the first two terms, that result, by the limit of this third term. So that gives us the limit as n goes to infinity of 1 minus r upon n, quantity raised to the n minus x power. So let's look at this. Well, that's nothing more than 1, if I were to combine this fraction, that's 1 over 1 minus r to the n, right, raised to the x power. Because here, if I say 1 minus r upon n to the n minus x is the same as 1 minus r upon n to the n power times 1 minus r upon n to the minus x power. Okay, so if I do that, well, that's just this term, 1 minus r upon n to the n power, times 1 over 1 minus r upon n to the x power. So it's a negative exponent. It's 1 over. Okay, so now I have this expression, and I'm going to consider my limit. Now, if n goes to infinity, well, n in the denominator gets really, really big. I have 1 over 1 minus r upon n to the x power. So that's really 1 minus r upon something really big as n goes to infinity, all raised to the x power. So constant r, it's a rate, divided by a really big number, well, that's 0. So I can replace that r upon really big n with 0, and I get 1 minus 0 to the x power. Well, 1 minus 0 is just 1. I exponentiate it, doesn't matter how many times, x many times, 1 times 1 times 1, however many times I perform that multiplication, i.e. the exponent, it's always 1. So I get 1 over 1 to the x power, that's just 1. So that second term goes away. So now I'm left with the limit as n goes to infinity of 1 minus r upon n raised to the n power. Okay, so now this term, this is just e to the minus r. Now this comes from a result called the Gaussian integral. Just take it on faith that it is true, because it is, and at a later time we'll prove and actually develop this Gaussian integral in another module. But at this juncture, I mean, you're welcome to look up the Gaussian integral. Just take it for granted, on faith that it's true, because it is true. This Gaussian integral says that this 1 minus r over a big number raised to that same big number is equal to e to the minus r. Okay. So we're going to take this limit and we're going to replace it with e to the r. So now for this third term, the limit as n goes to infinity of 1 minus r upon n to the n minus x power, that's e to the r, e to the minus r. Okay. So now our expression then becomes r to the x power upon x factorial times e to the minus r, where r is our rate. And we put them together. We put this e to the minus r. It's a negative exponent, so it's in the denominator. We get r to the x power upon x factorial times e to the r power. All right. So now, if we replace r with another variable, it's just a substitution. R is the rate, but we don't like r, right? We're going to write Greek letter lambda as a replacement for r. It's still the same rate, the average number of observations in each module of observation over time. So now we replace r with lambda. So lambda is equal to r because it looks nicer, and it's also in the literature. And so we get the probability mass function for observing x many occurrences of the event given a rate, average rate of lambda is just e to the minus lambda times lambda to the x power upon x factorial. And there's our probability mass function for the Poisson distribution. And so one of the things we're concerned of, here's our mass function for the Poisson distribution, is we want to show, goodness, well, is this a real probability? And one of the ways to show that, of course, is to show law of total probability is obeyed. And so we're going to sum together all of the different numbers of observations we can have for this probability mass function. So we're going to sum for 0 observations, that probability, 1, 2, 3, 4, and we're going to do that up to and including infinity. So we're going to sum together for x goes from 0 to infinity, probability of x for that mass function, p of x, and we're going to show that this sum for the Poisson probability mass function is equal to 1. And now you notice I called it the probability mass function. It's a mass function because this x, the number of observations of the event that I see, is countably infinite, right? You can draw a one-to-one correspondence with this number and the set of real numbers. And so what we're going to show then, if we sum together this mass function for all values of x, that we get 1. So this is where the Taylor series and Maclaurin series that we talked about last time comes into play. Now, the Maclaurin series is nothing more than a Taylor series evaluated at origin, or 0. And so for e to the lambda, the Maclaurin series is equal to the infinite sum, x goes from 0 to infinity, of lambda to the x power upon x factorial. And I will leave this to you. Given the scheme that we followed from MATLAB, I'll leave it to you to solve this yourself. It's very, very straightforward. And so we're going to take our sum and we're going to substitute, literally substitute for p to the x, p of x, and we substitute for p of x our probability mass function. So we have the infinite sum where x goes from 0 to infinity of p of x, so e to the minus lambda, lambda to the x power upon x factorial. So if we do that, well, or rewrite that so it's a little bit neater, we make the observation this e to the minus lambda does not involve this index on the summation. So for all intents and purposes, it is a constant underneath the summation, so we can factor it out. We do so, we get e to the minus lambda times the infinite sum, x goes from 0 to infinity, lambda to the x upon x factorial. And so now we're going to substitute in our Maclaurin series. The Maclaurin series for e to the lambda is just this infinite sum. All right, so here we have that same infinite sum. So we're going to substitute it in e to the lambda for that particular infinite sum. So if we do that, we get e to the minus lambda that we had, our leading coefficient we factored out, and we have that substitution e to the lambda. Well, that's just equal to 1. And there's our proof. And so we've demonstrated that this probability mass function for the Poisson is a probability because it obeys the law of total probability. The sum of all of the values of the probability for all instantiations of x is equal to 1. And we arrived upon the mass function for the Poisson distribution by taking the binomial and treating the number of trials as infinite. For every moment in time, we evaluate, is there an event, is there an event, is there an event? Yes, check, we have an event. And so the Poisson is nothing more than the binomial with an infinite number of trials. And it is a probability because it obeys the law of total probability. Okay, and there's our result. So with that, we will end there. Next time, we will finish our conversation on the Poisson by developing and deriving the expression for the mean for the Poisson distribution and the variance. And then we'll transition to so-called continuous distributions. So again, please make sure you're keeping up with the reading, and the reliability simulation is due on Thursday the 29th. With that, as usual, please stay healthy, stay safe, and I'll see you all on Thursday.